talk of the day. Yeah. We're going to get you out of here soon. I'm William. I'm from North Carolina. It's 1,700 miles that way and 5,000 feet straight down. I build machine learning systems at Grubhub, part of a delivery team, so I work to deliver food all around the country. Previously, I worked in internet security and built sonar systems. And now I work to deliver food and also do amateur slide illustrations. So Grubhub, American company, we do online food ordering. We do delivery, we do self-delivery, which is what I work in, where you can order food and get it delivered via a bike or a car or scooter, no drones yet, as far as I know. So the problem that we are trying to solve is that every week we schedule drivers for time slots. So you look at this little illustration, you can think of it as, we know food peaks around lunchtime, then dies off, then you get a big spike around dinner time. So we schedule drivers to be on the road in order to meet that demand. If we schedule too few drivers, then you, the diners, are unhappy because your food doesn't arrive on time. If we schedule too many drivers, Grubhub's unhappy because we pay out a base rate. The drivers are unhappy because they're sitting there making the base rate instead of more for actually delivering. So to solve that problem, we try and predict into the future how many orders we'll get at any point in time for all of our regions around the country. And so my team owns and runs that product, which we have called order volume forecasting. So what that looks like is every day, we have this large batch job where we pull in all of our historic order data for all of our regions, weather data, sports data, promotions, the phase of the moon, anything you could think of that might influence how people order food. And then we train a series of models for all of our regions across the country, and we predict into the future several weeks how many orders we'll get. So here's an example of a predicted time series out for a week, and you see you got a lunch peak and a dinner peak, and then nobody really orders food between 4 a.m. and 7 a.m. And we do this every day, and this takes quite a while. So you can think of, for all of the models that our data scientists build, and certain models work better for certain regions, and for all of the regions we have across the country, we're training models and doing these predictions. The situation becomes even more complicated if you, as a data scientist, want to, say, do a back test against the last year of data we have. Then suddenly your problem increases dramatically in the amount of compute you're trying to do. So when I started here, one of my first tasks was, well, how do we parallelize this to take better advantage to the clusters of machines that we have? So the design goals going into this were, one, we really preferred to work in Python. That's what the data scientists are using to design models. We wanted to reduce any headaches of trying to translate that into another system. We preferred them to be Pythonic. It's nice to not be fighting with your APIs and as you're building these things. Two, we preferred simplicity. The less moving pieces and new sources of software that we had to deploy, the better. We thought it was important that we were able to do local development, say on your laptop, and then be able to deploy that nearly as directly as possible to a production cluster. And then fourthly, important for me, coming into this new code base, as not having seen any of it before, is that I really didn't want to have to totally disassemble it and rewrite it into another framework for distributing this work. And it's also important to note that our particular problem is heavy compute. I wouldn't call this a big data problem in our case, and that our data fits mostly on a normal laptop's memory. But really, we're trying to do a lot of compute in order to train these models for all the regions. The contenders for doing this work were Celery, which I like because food reference, Apache Spark, and then Dask. Ultimately, we chose Dask to see if it would solve our problems. And we liked Dask for several reasons. One, it was a very familiar API. It's often modeling existing Python APIs for doing parallel processing. Very easily scales out to clusters of machines, and also allows you to run parallel processes on a single machine. It also either directly integrates with the existing Python ecosystem or directly uses it. So pandas and Scikit-Learn and NumPy are all under the hood for doing the heavy lifting in most cases. It supports complex applications if you're trying to create this crazy graph of workflow for jobs that feed into other jobs. It's simple to do that. And then from not necessarily the responsive software, but responsive maintainers, very easy to get in touch with the people writing the software, and they answer questions on Stack Overflow and in the GitHub issues quickly, which has been nice. And here's a quote from Matthew Rockland, who created the library, just calling out the different use cases here, where if you're trying to do computational graphs, you might be considering Celery or Airflow, or maybe you're dealing with big data issues, like using Hadoop or Spark. All of those, Dask can essentially work in those cases. So when you're looking at the use cases for the library, it's important as you look at how people are using it. There's two main cases. One, big data. You're working on large arrays where maybe you're previously had worked with a database or with Spark. Dask has an array and a data frame and a Dask bag APIs. And then in our case, we're much more of the custom task scheduling, where previously maybe you're using Airflow or Celery. That is also a use case for Dask. So if you want to get started with Dask right now, you can do a pip install Dask, or my favorite, conda install. It will Python only. It's going to be using a lot of libraries that you probably already have, a pretty small footprint, which is nice. So as an example, say you're wanting to parallelize a function run across either distributed on one machine or many machines. You have some arbitrary function. In our case, this would be training a model. It takes some inputs, does some work, it spits some outputs out. You can take that function and you can use the Dask distributed components, where you're grabbing a client. The client will either connect to a local cluster or distributed cluster. And we're calling client.submit, which mirrors the concurrent futures API. And you pass it the function you want to execute, the input parameters. And in our case, the functions aren't pure, but if your functions were pure in that your inputs determine your outputs, Dask will aggressively cache those for you if you would like. And we're appending these into a list of futures, and then we're using this as completed API to wait in a for loop, and as the work finishes in whatever order it gets returned to you, you can pull the results. And if there's any exceptions that happened in your function, you can access those just like you would expect with a try except. So again, one of the design goals is to make sure that we could write software that looked the same whether it was local or distributed. So if you're running locally, you can use code just like this, where you declare a local cluster. You can choose whether you want to run threads or processes. Dask has an extensive page describing the cases where you would choose one or the other. You can control the number of workers dynamically, so you have a cluster.scale down here where you can add or remove workers as needed. And then Dask also does some memory checking, so if a worker gets out of hand with its memory usage, it'll kill it and restart it if you so desire. And it gives you a nice UI. This is only part of it. It shows all the workers, the amount of memory consumed by each worker, the active tasks. If you go to another tab in here, you can look at the stack traces of all your workers to see what they're doing at any given time, whether they're stuck, and progress for all the tasks, whether you had errors or the memory usage. So then, in our particular case, we have access to a Hadoop cluster using Elastic MapReduce. This works out of the box with Dask. You can log into your EMR cluster, you can pip install Dask, and you can create a distributed cluster. It will take advantage of Yarn, which is part of the Hadoop ecosystem, which creates containers with a certain amount of memory and compute cores. And it will also take advantage of HDFS for distributing files to those workers. That's also how the Python environments get distributed to each worker. So you don't have to worry about configuring each box with a specific Python environment. You can tell Dask, hey, this virtual environment that I'm in with the master node, zip it up, send it to all the workers, so you have identical environments, which is wonderful, in my opinion. If you don't have a Hadoop cluster, and that's fine. You can try Kubernetes. If you don't have Kubernetes, Dask has a whole deployment model using SSH. So any box you can SSH to, give it an IP address, make sure the ports are open. It will let you instantiate workers on all those boxes, and they will happily compute and return results. And there's Google Compute System, and essentially every cloud distribution has nice out-of-the-box use for Dask. Okay, so in our case, we're deploying on Yarn. I put all of this on this slide because I spent a long time trying to figure it out, so it may be useful to you. You can hunt up the slides later. But we're describing the workers that Yarn will be creating on our cluster. We're saying up at the top, we have some number of workers. Here's how they restart behavior. Here's how much memory and virtual cores we would like for them to have. This files declaration says, hey, maybe there's a file that I want you to send to each of my workers. In our case, we use that for distributing a data cache. So we have a SQLite database where we're caching data. And when a worker starts, we say, hey, Dask, make sure this file is on this worker before it starts. Then you can also declare which environment variables you want in each of your workers. And at the bottom here, it says, hey, make sure my scheduler starts before all my workers. Then you can just similarly describe a scheduler. You can package together into this application spec. And that spec object is what you send into your create cluster command. And it will automatically distribute those workers across Yarn and let you do something like this. So this is pretty much verbatim how we're using it, whether we're distributed on EMR with tens or hundreds of nodes or running it straight from our laptops, where in this case, we're iterating through some groups of regions. We're calling submit on this forecast function, passing some variables into it. Then we're waiting till they complete their work. We're grabbing the results and processing it in the exceptions that the models may have had during training. And that works locally or distributed. A few other nice-to-have things. It's nice in your logs to go ahead and print out your cluster user interface. We do that when the logging starts. You can pop that open, and I'll have a shot showing that. You can see all the workers, their current logs and statuses. Also nice to have, say you want to do some work on your workers before they are accepting function calls. In our case, we're using this to set up Python logging formats. You can give a worker callback, a function that you want run on each worker as it starts. Similarly, I believe there's a shutdown callback you can use for doing any cleanup work you might want. In our case, Yarn handles the logging, so any standard error or standard output from the Python functions will be gathered together and sent into Hadoop's standard logging. There are other recommendations if you're using different deployment methods, and Dask has decent documentation about that. There's a shot of what it looks like when it's deployed on the cluster, showing all the workers, and you can drill into each one and look at their individual logs. Finally, we found it very helpful to write some light wrappers. I've included those in the appendix here so that if you want to completely disable Dask, you can do so with an environment variable, and it will run in serial mode, which makes debugging much easier. And those are just some simple light wrappers around the cluster and as completed functions. For those of you that are using more machine learning tasks, just a couple of notes here. There is deep integration with Scikit-Learn so that you could wrap any of your Scikit-Learn tasks with this parallel backend using Dask. And it will take over joblibs functions. So any models you might use where you have n cores equals, it will distribute those to Dask workers. Additionally, any functions that have a partial fit can also take advantage of being distributed to Dask workers. And if you're using, say, XGBoost or TensorFlow, it will intelligently break apart your data and hand it into XGBoost and TensorFlow's existing distributed deployment models. And then if you're working in areas where you have large amounts of data, Dask essentially allows you to work just like you would with pandas using their data frames, which is essentially pandas with some Dask magic on top. It breaks apart the pandas objects across the workers. Same thing with NumPy arrays. It will break apart NumPy arrays and manage those intelligently across the workers. And if you have unstructured data, there's a Dask bag API, which looks functionally equivalent to how you might work with RDD and PySpark. So the takeaways, it worked well for us. Forecasting is able to scale with our number of compute nodes on our cluster. So we can arbitrarily choose how fast we want to run it. We can do back tests in much shorter time. Even on a single node operation, we improve things by about 50% in terms of the time, just by being able to distribute some of the training. If you are doing any sort of distributed compute, I would recommend taking a look at Dask at least. It may not solve your problem, but I think it's a good first place to try, rather than some more complex things. If you're using Yarn, it does complicate matters. Most of my time was spent figuring out Yarn. I don't know that Kubernetes would make that easier for you, but something to keep in mind if you're estimating effort. The Dask website has great documentation. It's a fun read, just the way they write. They have a nice page comparing Dask to other solutions that's worth reading through to get a sense of how they think about problems. And as I mentioned, you can get on Stack Overflow and get an answer from any of the maintainers, usually within the day. And also to know, it's a complex library. There's a lot of different ways you can use it. And so if you look at how people are using it, keep in mind that the vast ways you can use it make it non-obvious sometimes whether it will suit your use case. So it's something you got to get in and play with. Finally, Grubhub's hiring. If you want to come work with me or not with me, let me know. So thank you. I will take questions, but I'll do it offline so the rest of you can go home.